A lot of cases, the pattern is pretty easy, like take a bunch of red and then a bunch of blue, and that's it. So there are lots of different ways lower bounds have been constructed. And upper bounds, in some cases, we're doing a brute force search, which can be very difficult, as you know. So for us, the two methods I'm going to refer to as we talk about the results in the next couple minutes, a custom-built parallel backtracking algorithm. And what that means is we test all possible colorings, but not in the dumbest way possible. I won't argue that it's the best, but it's not the worst. And by being parallelized, basically we just divide up the work to make things go a lot faster. The other way we're going to solve some of these problems is using satisfiability. The idea is to say I have a coloring of length n with no monochromatic solutions is one very large logical statement, right? If I break it down into its component statements, what I'm saying is, for the equation x plus y equals z, 1 and 2 are not the same color. 2 and 4 are not the same color. 1, 3, and 4 are not all the same color. And combining all of those statements into one gigantic logical statement, and then asking whether that statement is satisfiable, is the same thing as asking whether a valid coloring exists. Does that make sense to my logically minded friends?
This is NP complete.
Yes, in general, SAT problems are NP complete, and in general, Rado numbers are not easy to find in any way. So there's a nice marriage of difficult problems here. So we'll start with some two-color Rado numbers that we've managed to compute. So here's an equation that doesn't fall under the auspices of any previous theorems. And I managed to compute, I think, more terms than this. I ran out of space. I don't think I want more space on the slide for blocks of numbers. So here we can see there's sort of a weird, it's almost increasing, but not really. But we do have, at least conjecturally, evidence to support that it's about that big, k squared over 9. That would be in line with some of the previous stuff we've seen, where it was k squared over 1 or 4 or 9. What's interesting is that putting 2's in front of there doesn't affect sort of the growth. Similar example, and this one I think is a bit more interesting because it only has 3 variables, is to take kx, k plus 1y, k plus 2z. So here, if you want to think of this as A, B, C, in the most general 3-variable problem, ax plus by equals cz, I'm taking sort of a weird section of that problem, where A and B and C are all consecutive. And here, I don't know why I can't prove it, because I've really tried. I have all of the colorings that prove these lower bounds. These are exact, but as lower bounds, I have colorings of length, whatever this is, minus 1, and they don't have a pattern. They don't have an obvious pattern that I can just emulate in a proof. But it's very clear to me that this is the correct number, and we just need to prove that. We can also
What do you mean they don't have a pattern? Is
So-
that the pattern?
So what I'm saying is, to prove that this is 10, there's a coloring of length 9. And to prove that this is 17, there's a coloring of length 16, and so on. And those colorings don't have an obvious structure
Oh, I see.
that just
Has
generalizes.
a number.
Oh, I see. Has a
Yeah.
number.
The numbers have a pattern, the colorings don't. And if I can find a way to make that work,
They may have a pattern, but it's not
Right.
smart enough to see.
I haven't seen it yet, right?
So do you find all possible patterns or just one that
All of
works?
them, yeah.
Okay.
So because this is an exhaustive search,
And how many are there?
a lot. I mean, as you go, obviously you get more, but there are a lot. And sometimes I don't know which ones to think about fitting a pattern, but there are lots of them that I could choose, but none of them seem to have a good, obvious structure.
And they're never unique.
They are for lower
Yeah, but no.
ones, but as you go, you'll often find that in a coloring of length 150, there are 10 numbers that are irrelevant in some sense, or mostly irrelevant, and they can be colored in any possible way, which is 2 to the 10th. Even though they're irrelevant, they bloat the number of colorings.
Is that 15 the right number?
Yeah, I think so. I hope so. Yeah, so it's not increasing, which is, so when I wrote this question mark equals, I'm sweeping under the rug. It doesn't start being equal to that until like here. So the first couple terms don't agree. So it's eventually equal to this. So I can also compute off-diagonal Rado numbers, which I'm just going to throw a table at you and see what happens. Ready? So here's an equation that's well understood, not off-diagonal, so the diagonal of the table is the diagonal ones. So those are known, but the rest of the table, which is symmetric, which is why I've only filled in half, is not known. And what I've managed to do is get formulas for a few rows, and I don't remember if I got any diagonals of this. Maybe not, but the first couple rows haven't been too hard to figure out. But it would be nice to get a formula for the whole table. And I'm still looking into that. Here's where we get our first, I think, really significant result. And this was sort of an accident. I filled in this table, and then I realized that I had proved more than I thought. So taking this equation here, so it's generalized sure numbers, but I've added a k here on that last one. So k goes to the right, m goes down, and I computed these values. That says Rado, that is the wrong thing. They were computed using the other method. So forget that says Rado, it says the other thing. And one thing that we know is that these lower bounds here for generalized sure numbers, right, if k equals 1, then it's just the normal version of that, were given in that paper in 82. So m cubed minus m squared minus m minus 1, which is nice because it looks like the m squared minus m minus 1 that we saw before. One thing that's interesting is we think that it's true for these 3 color numbers, but we don't know. It is true for the first 4. Those are correct if you plug them in. It is not true for 4 colors. So it's already wrong if we go higher than 3 colors. But the question is, can we say anything about these numbers? And the answer is to think back to the one theoretical or general statement I made before. So does anything strike you in this table? I'm asking the audience for help. Charles?
It seems like the k equals 2, m equals 5 spot to be 173.
Yeah. And you can see that along this diagonal, they are all 94. I have a pointer. These all probably are 173, and in fact, they have to be. Because if I take something with m variables, and I take, say, this second to last guy, and I set it equal to the last guy, I've decreased m by 1, I've increased k by 1, which is moving up the table. Which tells us, even here, 889, this number is at least that big. But all the way up this table, this is the biggest one possible. So the whole table gets filled in.
Assuming those lower bounds are tight.
Yeah, which they are. I mean, as lower bounds, they're tight. We don't know whether they're tight as upper bounds until we compute sort of the other side of this table.
Oh, okay.
So all of these italicized numbers are sort of implicitly computed by computing these, which does in fact verify the tightness of this m cubed minus m squared minus m minus 1 for 4 more terms. And I do think that with a little more work, I could keep at least attempting to verify it. Although if it fails here, right, if the next term here is bigger than the term here, that doesn't mean it's wrong, because it could be that as you move up this diagonal, it goes up a little bit. Here are some 3-color off-diagonal Rado numbers, which I just made up an equation, x plus ay equals z, and These are very hard to compute. Some of these took a long, long time, many days to fill in this table. In fact, I think the entire computing time for all of these was roughly 3 weeks on, a giant computer full of small computers. So this was not an easy set of numbers to compile, and what is frustrating is that there's no polynomial or anything like a polynomial that seems to fit these data. So maybe I need more data, and if so, I might need a bigger computer. But these in and of themselves are interesting because, of course, we don't have any guarantee that the 3-color Rado number should exist. Although for each of these, the 3-color number does exist.
Now we do.
Now we do for these,
Yeah.
but maybe for 6 it fails. I don't know, but because we have a 1 here and a 1 here, those two coefficients, if I rearrange it, so the 3-color number still exists, and I suspect that that should mean that the off-diagonal 3-color number exists. So I think this is safe, but no guarantees. And we're going to stop at 4 colors. This will be our last number of colors. So for 2 colors, the non-homogeneous sure numbers are 4c plus 5. There was a different case when c was negative, but I'm not going to worry about that. Here, similar for 3 colors, 13c plus 14. And one thing that's a little bit frustrating is it's not going to be quite the same if you look at the data, because these numbers are not quite linear. If you check the differences, they're 40 after some time, right? But the first couple differences aren't quite correct. So instead of trying to deal with what is going on here, because I'm not really sure why it's not exactly 40, I decided to prove this instead, which is at least a lower bound with this sort of linear pattern. So for any number of colors, you get the same as you saw before. So here, if you plug in 4, you get 81 minus 1 over 2, which is 40. If you plug in 2, you get 4, which is here. And you'll notice it's plus 5 here, 13, 14, because of this plus 1. And what that really means is ignore the plus 1. I'm going to block it out. The goal is to make the coloring that long that's valid, because then the Rado number has to be at least 1 more than that. So we know it for 2 and 3 based on previous proofs, and inspired by that, I just basically took that idea and continued it. You take the previous coloring, which we have at least a couple, and you take 2 copies separated by the largest possible string of the new color that you could. And how long that is dependent on C. And that's where 3 to the r minus 1 over 2 comes in. That just basically comes from the longest length you could possibly put in the middle. Now, by induction, this has to also be valid. There's nothing of monochromatic in the first chunk by induction. The previous coloring should be okay. In the middle, we pick it to be not too long, so there are no new solutions of this new color. And what happens is x, y, and z can't all be in the end, because they're too big. So what happens is, if you think, I'm just going to start waving at this. If you think x is here, and y and z are here, if I translate y and z down, they're still solutions to the equation. Because 1 on one side and 1 on the other side, I can move them around. So by taking y and z from here and moving them down here, I'm guaranteed that they shouldn't have been the same color, because they weren't when they were here, so they can't be when they're up here either. And I strongly suspect that for sufficiently large C, this is tight. We know it doesn't work for all C greater than or equal to 0. We saw in that table 2 of the values were wrong. But the rest, it seems to work. So I'm going to breeze through, because we're low on time. some of the nonlinear equations I've managed to talk about. We'll start with a weird nonlinear equation, which is a polynomial if you multiply things around. Rado proved, and I don't have a date on this because it's not published anywhere, that this equation is regular. And I can give you the two-color number for that, and for this, and for 5 variables, and with 6. I won't write those out, but you can keep going. And these computations are very difficult, not only because of the nonlinear nature of the equations, but because they have up to 6 variables. With 7 variables, no chance. One big open question is whether this Pythagorean equation is regular or even too regular. If so, I can show that it's at least 6,500 by giving you a lower bound. And in fact, if you think tweaking the equation will help, it won't, at least not in this way, because I can give you bounds for k between 2 and 20. And if you do like a different number between x and y, I can also do those. If you throw away all of the solutions and only look at relatively prime solutions, the set I can prove is not too regular, so it's infinite. So whether that can be translated into this being infinite, I don't know, but it's something we can prove.
You believe that it's false?
I'm pretty sure it's infinite. I have a bad feeling. It hurts me to say that, but I really don't know. So what I can do is if I take a squares and b squares and add them up and set them equal, I can prove a bunch of different numbers, just not with 2 squares equals 1. So here are some computations, and in fact, here's a theorem. If a and b are relatively close to each other, so b is between a and a constant times a, then the Rado number, two-colored.
Is it squaring on the x's or also the y's?
Aha,
In the second.
you got me. There's a typo that I didn't catch. The y's should also be squared. Yeah, sorry about that. So, yeah, they're all squares.
It says sums of squares.
Sums of squares, yeah. The title is correct. So here, I can prove for an infinite family of them that the number is finite and in fact uniformly bounded. If I tweak the constant c to be better, the constant m gets a little bit worse. Here's a proof that it's less than 9. And I won't tell you the details, the idea. This is all possible colorings, and I can tell you that these colorings are not valid because when you get to, for example, right here, 3, 6, and 9 form a solution where sums of 3s, 6s, and 9s are all equal. And how many of those I need tells me the constant c. Here's a bunch of data where this 9 is sort of pretty apparent. 5 sometimes appears, but 9 certainly appears a lot.
And that question mark,
That's Pythagorean equation, 2 and 1. So I don't know that one. But the 5s and 9s are all over the place. And the last example, which is sort of an interesting theorem of Hinman, is that if you color the integers, there's an infinite set where all of its finite non-trivial sums are monochromatic, and all of its products too are the same color, which is amazing and crazy and way beyond what my brain comprehends, because that's way more than one equation. That's many equations.
It's not in existence. It didn't come up.
Oh no, there's not a lot you can say about it. The proof uses things from logic, ultrafilters and other kinds of stuff that is far afield from what we've been able to do, but we can take that and sort of run with it. So here is a sum and a product, and the Rado number for both of those is 39. I can do it for 4, 5, and 6 variables, and I can even do it if we assume that the variables are distinct. Graham assumed that they were distinct and got a different number, which is much greater than 39, and I one-upped him by doing 3 variables with this enormous number. So just to give you an idea, we still need to know all of these things. If you know what these are, please let me know. There's a joke on this slide, Tom. Where's the joke? not that one. And what I'm looking for are new methods that might be able to do these things faster, because we're right at the brink of being able to compute these. We're very close. We can solve very similar problems, so better methods might get that. Other different directions, can we actually get a new theorem telling us what it means to be 3 regular, or 4, or 5, or 10? Are there ways to relate different equations to each other, because we don't have a lot that tells you something about 2 different equations? Maybe the number of variables is important. And there are lots of other types of Rado numbers. You can do a rainbow Rado number where all the solutions have to be different colors. You can enforce a condition where x and y and z have to be distinct, like in the last slide. You can do inequalities or other kinds of algebraic restrictions. So lots and lots of things we could still do. Most of these tools work for those, and I have not done any of this. So lots more to do. And the challenge remains, if you get a picture of an old guy thinking, put it in a slide, and it'll make the problem look really hard. So if these 3 guys couldn't solve it, maybe someone else can. We'll see. Thank you very much.
Maybe you.